Ethernet communications in the industrial sector is on the rise. The advantages in speed and accessibility over serial communications are making it the new standard for industrial communication. Industrial automation protocols have several methods of communicating. When devices from different automation suppliers need to communicate with each other, specialty communication interface products are required. Selecting the ideal method depends on your specific application requirements. If the best method is not used, problems can develop later that could negatively affect your bottom line. This video will discuss specific application examples that should help you understand how to select the best method for your application. We'll be using our products in these examples, but the principles apply to all Ethernet-based automation communication solutions. We'll begin by defining what the different methods are. Most industrial automation protocols have two methods of communication. There's client-server data communications and input-output message communications. Each of these methods has its own properties and characteristics that make them suitable for different applications. Both are used to read and write data between devices. I/O messaging is used when communication timing variations are not acceptable. Client-server data communications are used when some variation in communications is tolerable. Clients are devices that initiate communications, and servers respond. Clients cannot talk directly to other clients, and servers don't talk to other servers. It's possible for a PLC to act as a client, a server, as well as an I/O messaging master simultaneously on the same network, communicating with various server devices and clients while controlling remote I/O devices as applications demand. I/O message communications are given higher priority by the processor, while client-server data messaging are given lower priority. I/O messages are designed to run at regular time intervals, meaning the communication speeds are consistent, whereas regular data messaging speeds are dependent on the availability of unused processing power. SCADA hosts or HMI terminals, on the other hand, are almost always configured as a client. Other devices such as drives can act as a server or as an I/O message slave, whereas remote I/O racks primarily act as I/O messaging slaves but can act as servers depending on the protocol. To illustrate the dynamics of these different methods of Ethernet communication, we'll run through some examples of devices configured in each of the different methods we've just discussed and examine the benefits and other considerations of using those methods. We'll begin by taking a look at a PLC that talks Ethernet IP that needs to communicate with an HMI that talks Modbus TCP. For this example, we'll use a ProSoft gateway to exchange data between the two different protocols. The design goals for this example is to have data communication speeds of no slower than 500 milliseconds and access to the communication diagnostics through the PLC. The HMI is a client, and so we'll have to configure our gateway as a Modbus TCP IP server to communicate with it. In this case, we'll make the gateway a server on the Ethernet IP side as well. This means we'll need to use message instructions in the PLC program to communicate with our gateway. The client messages from the PLC will be sent with a lower priority, only executing once all the I/O messages have been completed. In addition to this, it should be pointed out that PLC message timing is dependent on ladder code execution. So regardless of having a lower priority, the messages cannot be sent faster than it takes the processor to cycle through the ladder file. As a result, there is potential for this arrangement to have some variation in communication speed. This is acceptable for this application because HMI communications will not be outside our requirements of under 500 milliseconds. By using message instructions in the PLC, we also get diagnostics on the gateway's communication that can be monitored using your PLC programming software. Having access to this data can greatly reduce your time spent troubleshooting in the event of a communication problem. Having our gateway acting as a server and the PLC as a client, however, requires that you make changes to the PLC program code. For our next example, we'll take a look at a PLC that talks Ethernet IP that needs to communicate with an OEM's PLC that talks Siemens Industrial Ethernet. In this example, we do not want to edit the program on the OEM PLC. We'll need fast data transfer of no slower than 50 milliseconds and be able to diagnose communication problems using the Ethernet IP PLC programming software or an HMI that's communicating with it. Editing the program in an OEM's PLC to initiate data transfers could void the warranty, performance guarantees, or you may not have access to the programming software. Therefore, for this example, we will use our gateway as a client on Siemens Industrial Ethernet in order to communicate with the OEM PLC acting as a server. When our gateway's port is configured as a client, it has a poll rate that sets your communication update interval and does not get sent at a lower priority like a PLC client message. This gives you fast, consistent communications. Like before, we could use message instructions in our PLC, acting as a client to communicate to the gateway as a server. But our Ethernet IP communication speeds will be dependent on the timing of the PLC's ladder code and any other Ethernet IP communications that may be going on. Getting data transfers in under 50 milliseconds could be difficult. To avoid using message instructions, we could configure our gateway as a client on the Ethernet IP side and the PLC as a server. This would eliminate the dependency on ladder logic timing and would also not require program changes. However, because the gateway is initiating communications, the PLC will not have any indication in case of a communication failure. The gateway would be invisible to the PLC. So if anything goes wrong, like someone accidentally powering down the gateway, your client device will simply stop communicating. This could extend your downtime when trying to isolate the problem, especially if the problem happens 5 years from now when the person who programmed it is long gone. The solution that meets all the application requirements would be to set up I/O messaging between the Ethernet IP PLC and our gateway. When PLCs do I/O messaging, sometimes called an I/O connection, they require a communication update interval to be set. This will ensure the communications between the PLC and gateway are fast and consistent, as they will be given priority over other communications. The PLC will also have access to communication diagnostic tags, which allow you to use your PLC programming software to troubleshoot problems. Instead of using our gateway, our in-chassis communication module could also be used to solve this application. Our in-chassis modules use I/O messaging across the backplane to the PLC. The module's communication port would be set up as a client to talk to the OEM PLC, and this would meet all the design goals for the application and give you a more integrated solution. In this next example, we'll examine a situation where we have two PLCs that need to do high-speed interlocking. One PLC talks Ethernet IP and the other talks Profinet. This application requires the communications to have extremely tight timing. For this example, the PLCs are able to make calculations and issue commands in real time based on data they share with each other. In applications where every millisecond counts and when the protocols support it, using the I/O messaging method is the best way to go. By configuring an I/O message on each side of our gateway, we can ensure communication speeds between the PLCs as low as 10 milliseconds. We also need to be able to use the PLC programming software, or HMI, to view and troubleshoot communication issues. The thing to know about this method of communication is that it is very deterministic and repeatable, thus offering very fast and precise timing. The data transfer rate is locked in by the program, and I/O messages are given top priority by both PLCs. Using this communication method requires you to program both PLCs to set up the I/O messaging. This will also allow the PLCs to monitor the communication status of our gateway and display the diagnostic tags to an HMI or the PLC programming software. For our last example, we have a PLC that needs to talk to 5 drives that use a different protocol than the PLC. In this example, the PLC talks Ethernet IP and the drives talk Modbus TCP IP. Modbus TCP IP doesn't use I/O message communications, so we'll need to use client-server communications. The PLC will have to be a client as the drives will be server devices. Our design goals here are high speed, fault tolerance, and communication diagnostics in the PLC. This PLC can use a message instruction and some ladder code to create Modbus TCP packets via their Ethernet communication module. Using this method has some shortcomings. PLC data messages are sent at a lower priority than I/O messages and can be affected by other Ethernet messages, like if a user performs a program upload. So using this method, the communications to the drives will likely slow down periodically. For this application, a dedicated communication module that has Modbus TCP IP built in is a better solution, as it is not affected by these issues. A single client has no problem communicating with several different servers on the same network, but there are some considerations using such an arrangement. The client will open communications with each drive one by one, sending a read or write command, and waiting for a response. Once the client receives the response from the server, it will close the connection and move on to the next drive. The issue is if one drive is taken offline unexpectedly, it will slow down communications with the 4 other drives while the client waits for its requests from the missing drive to time out. Some server devices also have limits on how quickly socket connections with the clients can be opened and closed, meaning the client could have to wait until an individual server is ready to resume communications. The ideal situation here would be to use a communication module that supports multiple clients, one talking to each of the servers. This will ensure faster communications by giving each drive a dedicated connection to a Modbus TCP IP client. Commands can be sent to all 5 drives by separate client connections instead of cycling through each drive one at a time. In the event of a drive going offline, communication with the other 4 drives will remain unimpeded. Many devices, such as ProSoft's MVI56E MNetC, can support multiple client connections. Also, because our module uses an I/O connection to the PLC, the communications are fast and the PLC has access to communication diagnostic tags to reduce your troubleshooting time in case of problems. So, in summation, when deciding what communication method you want to use, there are a few things you should consider. You should be mindful of what devices you're using, what protocols you're using, and whether or not you have access to the PLC program. The devices you have will determine what methods you can use. Remember, some devices can only be configured as a client or as a server. Also, not all Ethernet-based protocols can support I/O messaging. They will need to use client-server communications. Finally, if you want to configure our in-chassis or gateway module as a server or utilize I/O messaging, you will have to make edits to the PLC code. If you don't have access or don't want the hassle, it will have to be configured as a client on the network. ProSoft Technology offers a wide range of Ethernet communication solutions for the industrial environment. Our in-chassis modules and gateways give you the power and flexibility to handle whatever communication needs you might have. To learn more, visit our website at www.prosoft-technology.com.